Hello and welcome to this Asteroid Day special presentation called Planetary Defense. Are we ready to protect Earth from asteroids? My name is Karl. I'm a space engineer from Germany, and in my day job I work with the International Space Station and support the astronauts and the European centers perform the experiments. But at night or on the weekends, I'm involved with planetary defense since over 10 years. So I would like to share a bit what that is all about. And I would like to thank the Planetarium of Brussels for giving me this opportunity to present this overview to you on the occasion of Asteroid Day. Asteroid Day, as you can see on the logo, it's celebrated on the 30th of June. And the question, of course, is what happened on the 30th of June? We have to go all the way back to 1908 to Tunguska in the middle of Siberia, where, to the best of our knowledge, a meteorite exploded in midair and leveled almost 2,000 square kilometers of forest. Luckily, as far as we know, nobody died. Back then, the explosion was felt and seen far and wide. And it took 20 years to send an expedition to the impact site. No impact crater has been found, no material. So there was for a long time a debate what happened really, and there are crazy conspiracy theories out there. But the most likely explanation is indeed that an asteroid entered our atmosphere and then exploded over the place. And the United Nations a few years ago, they declared the 30th of June International Asteroid Day to raise awareness about asteroids. Here is a list of signatories of the Asteroid Day Declaration. And you will see astronauts, famous entertainers, co-founder Brian May, for example, the guitarist of Queen, is involved, and a lot of other people. And the idea is really to encourage everyone to pay attention to this topic and make sure that we are prepared for potential asteroid impact. That this is still a relevant topic was demonstrated back in 2013. Some of you might remember this because it was all over YouTube. In Chelyabinsk, Russia, another meteorite exploded in the air. This one was luckily smaller than the one in Tunguska. Tunguska was about 40 meters, 50 meters in size, and this one here was 18. And yeah, you might have seen the pictures. It left this trail of smoke on the sky, and we were lucky. It came in quite in a shallow angle, so all the energy was dissipated high in the atmosphere and did not reach so much to the ground. It did reach the ground, of course. So on the left, you can see the impact crater, if you want. So it fell into a frozen lake. On the top right, you can see the largest object that was retrieved by divers. And it weighs around 500 kilograms, if I'm not mistaken. But also a lot of smaller particles have been found, like the ones below in the snow. And even though it fell into a lake and most of the energy dissipated in the atmosphere, it still made some damage. I'll try to show you a video now to show you why that is. So people go out, look what's been happening. And then the shockwave hit. So you see, of course, the shockwave smashed windows, and some walls collapsed. And so, because people were like curious, they saw a light in the sky, so they ran to the window to see what's going on, and that's when the shockwave came, and that's where most of the injuries came from. There were about 1,500 people who got injured, and most of them were cuts from glass and the like. So the lesson here is for you: if you ever see something like that in the sky, don't rush to the window. Either take cover until the shockwave has passed, or try to stay in a safe place because there might be shockwave coming. This is nothing so very unusual. What is unusual in that case was that it was bigger than usual, and it was filmed. So here you see a distribution, and you will see it's all over the world. There is no spot that is safer or more dangerous than any other. And you see Chelyabinsk is the red dot over Russia because it had the most energy. But this happens frequently that some meteorites enter the atmosphere and release the energy. We also have meteor showers, so like shooting stars, but those are usually the size of a grain of sand. So there you can see the distance. So you can see the nice display of light. But anything bigger than that enters the atmosphere, burns up, and if it's big enough, also makes a small explosion. If it's really big, it will hit the ground. And this map shows the location of all the confirmed impact craters on Earth that we have from asteroids. So this is where an object actually hit the Earth and made a crater. And you can see, again, they're all over. It's the Earth is special in terms of weather effects and erosion effects, that with time those craters get basically disappear, so you don't see them anymore. The ones you still see look like this. So we have the big picture on the left. That's actually the Rutherford crater in South Africa. It has a diameter of almost 300 kilometers, and that happened 2 billion years ago. So that was, I think by now it is only the second biggest impact crater on Earth. There was a bigger one discovered recently in Australia. And even though this has been a very long time ago, there's still evidence for this. You have a smaller one, the upper left. It's also in South Africa. That's about 1.5 kilometers in diameter, which is the same size as the crater on the upper right. That's the famous Meteor crater or Barringer crater in Arizona in the US. This was caused by a 50-meter iron object about 50,000 years ago. And then below you have another crater in Canada, or at least what's left of it. So you can see that with time, craters disappear. Maybe the most famous one you might have heard about is, or asteroid, is the one that killed the dinosaurs. So 65 million years ago, there was an object with at least a size of 10 kilometers. So that's really big. That hit the Mexican Peninsula. The Mexican Peninsula. And because of all the dust that was ejected, the sky darkened for 3 years, even though the latest models I've seen. And so because of this darkness, all the plants died, and therefore also all the animals died. So 75% of species went extinct back then. And that's, of course, something we would like to avoid. It doesn't happen only on Earth. Here are other examples from the solar system. On the top left, you see the moon. There is no erosion, so all the craters are preserved, which is great to study them. This is also why we know that in the past, when the solar system was younger, there were more impacts than there now. So for us, that is good news, but there's still some out there. For example, the picture on the lower left, that's a fresh impact crater on Mars. Mars has a thinner atmosphere than Earth, so even smaller objects make it to the ground. But since we have satellites around Mars to take pictures of its surface, we're able to see changes. And this was one recent change where a meteorite impacted Mars. And another famous event occurred back in 1994 on Jupiter, which you see on the right. There, a comet broke up, the comet Shoemaker-Levy 9. That impacted Jupiter's atmosphere, and the shadows you can see where it impacted, they have about the size of the Earth. So just that gives you an idea of the size. Where do asteroids come from? They are mainly two sources. So you have the solar system, and between Mars and Jupiter, you have the asteroid belt. Those ones are fairly stable in terms of their orbit around the sun. But of course, from time to time, it's possible that through gravity disturbances, they might leave, or collisions, they might leave their orbit and then enter the inner solar system with chances of crossing the Earth's orbit. Further out in the solar system, we have the Kuiper belt. This is also like a collection of smaller objects. The most famous one is Pluto, which used to be a planet, but now is called a Kuiper belt object because there are thousands of these objects out there. And then even further out, we have the Oort cloud, and it's so far out we haven't even seen it yet, but we know it is there. And this is where the most of the comets come from. So if another star comes close to our solar system and there's some gravity perturbations, then one of those rocks enters our solar system, becomes a comet, and also potentially can hit any of the planets. Jupiter luckily acts a bit like a vacuum cleaner because it has the greatest gravity. So it attracts many of those comets and asteroids coming in, and either catches them or kicks them out. And so otherwise we would have even more in the inner solar system. How do asteroids look like? These are all pictures of asteroids that we have visited with spacecraft, and then in relation to their size. So you can see the huge one there, more or less in the middle. That's like almost 100 kilometers. And that's a big object in the asteroid belt between Mars and Jupiter. And then you have smaller ones that reach the size of objects that were responsible for the extinction of the dinosaurs, or others that we are actually worrying about. Since we do not want to end up like the dinosaurs, we keep an eye out for them. So we use optical telescopes and watch the sky. Of course, they're very small, they're very dark, so they're very hard to find. Nonetheless, we don't have a choice, so we keep looking. And this is what we've found so far. So all the green ones are asteroids in the asteroid belt between Mars and Jupiter. And green basically means they're safe. They don't come near the Earth, so there's no problem with those. All the red ones, however, they cross the orbit of the Earth and therefore potentially pose a threat to us. So those are especially the ones we want to keep an eye on. The good news is, so far, we can predict the orbits about 100 years in the future. None of those we know about will hit the Earth. So that's the good news. The not so good news is that there's still many objects out there that we don't know about, or we haven't found yet. We know they're there because they're modeled, so we can calculate how many of which size we can expect out there. And here you see the graph ordered by size. So again, the big ones, we're pretty good. So we found about 98%, I think, of the ones bigger than 1 kilometer. And just as a reminder, the one with the dinosaurs was 10 kilometers. So the big ones, we have an eye on. So that's good. The ones that are smaller, and remember the Tunguska events as well as meteor crater are caused by objects about 50 meters in size. They can still make a lot of damage. If that hits a city, that's a bad day. So we would like we would like to keep an eye on those as well. And we know there are many more out there, and that's why we want to find them. Because one of the things I find the most amazing about asteroids, if we discover them early enough, and early means about 10, 20, 30 years, the more the better, and we know they're coming our way, they're actually the only natural disaster we can not only predict, but prevent. Just compare that with a volcano. Even if you can predict, oh, this volcano is going to erupt, or here's an earthquake that's going to happen, there's nothing we can do about it. Asteroids, on the other hand, we can actually move out of the way. I'll explain later how that works, but this is what I find the most fascinating about this. So, summarizing the slides, there's still work to do because we want to find them all so we know when one is coming our way. We have other options. So here's a schematic of the inner solar system, and you see the inner planets. And in green, you have the orbit of an asteroid. And as you can see, some come close to Earth, which is actually also a great opportunity to study them. If they come close enough, we can use radar telescopes, like the ones on the left, and take radar images, as you can see on the right, and then you can see quite a bit of detail of the asteroid flying by. So you get a better idea of its shape. You can guess its composition, because some are made more from metal, others are more from stone, some are mixed, some are rubble piles, some are more compact. So it's the more we know, the better we can assess if there's a danger and what exactly there is that we need to do. Here's a close-up of asteroid Ryugu. So currently there are 2 science missions busy in the inner solar system. One is from the Japanese space agency, and that's probe Hayabusa 2 that flew to asteroid Ryugu. And also NASA flew to asteroid Bennu with its OSIRIS-REx mission. And interestingly enough, they have those 2 asteroids have very similar shapes and similar sizes. And what surprised the scientists most was how rocky those objects are. And you see a close-up picture in the middle on the top. And I mean, it's like you're standing at a riverbed and it's full of rocks. The Japanese actually took a sample, and you can see that on the bottom, the 2 left pictures. And it's currently on its way back, so the scientists can study like the composition and what it's made of, because asteroids can also tell us about the formation of the solar system. They're basically leftovers from when the solar system was formed. So it's very interesting also to find out what kind of chemicals and molecules are in there, because some of them even have organic molecules. So there is a chance that they help us understand where life or how life on Earth originated. The lower left picture also shows something very interesting. It shows a new crater, one that Hayabusa made. So they took two samples. One, they just grabbed some dirt from the surface, and the other one, they shot a projectile into the ground to make a small crater so they can get fresh samples from underground. One of the interesting things that happened was that the crater they made was bigger than they expected. And this is exactly why we want to study those objects more, because the more we know, the better we can decide, oh, what will happen if one is our way and it comes our way, and what we can do about it. Every 2 years, there's a conference. It's called the Planetary Defense Conference, PDC in short. And that's when about 300 experts from all different fields that are related with asteroids, from detection to characterization to deflection missions to political decisions to communicating with the public, to disaster management, and all those things come together, and they have an exercise so they can see how, if something like this would happen in real, how they would act on this, and see where they still need to improve, or what they need to change to get better, or if how things are working. The problem with asteroids usually is, even though once we've discovered them, for quite some time we won't know exactly the orbit. So there's always a bit of uncertainty. So if you look at the left, you see a typical orbit of an asteroid in blue around the sun, and it crosses the Earth's orbit. And if we zoom in on the right, we can see that there's this uncertainty region. So we know the asteroid is somewhere along this line of red dots. We need more observations and measurements to narrow down where on Earth it will hit, or as you can see, many of those red dots are even away from the Earth, or where it would miss. So therefore, observations are really important. And again, the more we know about these objects, the better it is. Let's say an asteroid is discovered that has a probability, like let's say, 10%, 20% of impact. So the red dots are on Earth, and that's currently the best estimate. What would happen then? At the United Nations have an Office for Outer Space Affairs in Vienna, in Austria. And they have the Committee for the Peaceful Uses of Outer Space there. And within that venue, a few years ago, two organizations were created. And also the UN General Assembly endorsed that. And that is one, the International Asteroid Warning Network. And those are basically people that work together and take all the observations that are happening all around the world, put them together, and then decide if there's a threat for Earth or not. In case there is, they issue a warning to the UN and the member states. And then depending what the situation is, then it gets escalated to see what other things need to be done. And then we have the Space Mission Planning and Advisory Group, and those get into action once the probability of impact reaches a certain threshold, depending on probability of impact, the size of the object, and how much time is still left. And they basically come up with ideas how we could stop that. Like they know that's usually a lot of space agencies are in there who have rockets available, for example, or other technology that could be used to deflect the asteroid. So how would that work? Here's an example on the top of asteroid Apophis in 2036. This is an old image. By now we know Apophis will not hit in 2036, so no worries here, but it's a good example. So you remember the uncertainty region, and it spans basically the globe. And if you project it on the map, you get this red line. It's called a risk corridor. And the asteroid can potentially hit on any point on this line. But without better observations, we won't know exactly where. And usually we don't have time to wait this long to know where it's going to hit. Because as I mentioned earlier, the earlier we find them, the easier it is to do something about it. But it gives you an idea which areas are affected. And then IWAN, so the International Astronaut Warning Network, and same page, the Space Mission Planning and Advisory Group, they get to work. They warn people. They work on options, what we can do. One option, well, simply speaking, so it's the lower picture. So you have your corridor about the Earth, around the Earth, and of course, as long as it hits Earth, it's potentially a problem. If the asteroid is big enough, it's a problem. It doesn't matter where it hits. At some size, smaller ones might be problematic for certain cities. Bigger ones are problematic for regions or countries even. And if you go as big as the dinosaurs, it's a problem for the whole planet. So this is really a problem on a planetary scale. So it's a global problem that needs a global solution. And therefore we come back to the UN, because technically all you need to do is avoid having the Earth at the same time and space as the asteroid, because that's when they hit. Since the asteroid is a lot smaller in comparison to Earth, it is easier to move the asteroid than the Earth. So basically all we need to do is either give the asteroid a push, so it passes the point in space where they both would meet earlier than the Earth and thereby missing it, or we slow it down a little bit so it arrives at its spot a little bit later. But the whole thing would be a geopolitical decision, because say along this line are countries that previously were not in danger of being hit, but by trying to move the asteroid over the limb of the Earth into space to miss it, they would cross over that country. Now, of course, there's always a possibility of things going wrong. Imagine something goes wrong when it's over another country. Then you want to have this coordinated beforehand. Otherwise, people might say, oh, this was not an accident, and you have a whole bunch of different problems. So this is definitely a geopolitical decision, and this is why it's good that we have those committees and those groups where in an international environment, people work together to figure out frameworks and guidelines how to do this. And even though we haven't found one that is coming our way yet, it's good to be prepared, because we don't have the time to argue who does what when the time comes. So this is something we'd like to be prepared about. Coming back to the actual technologies. Again, the goal is simply to either slow down the asteroid a little or to accelerate it a little bit, to make it a bit faster. And there's certain ways to do that. On the upper left, you have something that's called a Kinetic Impactor. You just smash a spacecraft into the asteroid, and by hitting it, you transmit an impulse, and that either, depending from which direction you're coming, pushes it a little bit or slows it down. This is a very imprecise action, since have to guess based on your models what the asteroid is made of and the angle you're going to hit it, how much energy is transferred to see if whatever energy you gave the asteroid is enough for slowing it down, for example. We have on the lower left, this is called a gravity tractor. So according to Newton and everybody else, I guess, two masses attract each other. So when the apple falls from the tree, of course, it's attracted towards the earth. But at the same time, also the apple attracts the earth just a little bit. Of course, the earth is a lot stronger than why the apple ends up on the floor. And the same is true here in space. So if we park a spacecraft close to an asteroid, of course, we need to use our engines so the spacecraft does not get attracted and fall on top of the asteroid. But if we can position it in a way that it's close by, the asteroid gets pulled ever so slightly in the direction of the spacecraft. And if we have enough time, say 20, 30 years, over this time span, this would be enough to slow it down and make it miss the Earth. And this is very precise in the sense that we can calculate exactly how much we need to pull on it to know what's going on. And going back to the Kinetic Impactor, there we slam in and then we have to measure again and see, oh, did it work or not? And then maybe we have to send another one. So and maybe that's difficult because as asteroids go around the sun, it might take a couple of years, which we might not have to reach it again. So again, the earlier the better. If it's really late, you have the picture on the top, and then you have to use a nuclear device. There's a lot of discussion about launching nuclear weapons into space. First of all, it's by the Outer Space Treaty, it's not allowed. Second, of course, there's always the danger, what if the launch goes wrong? And a bunch of other political discussions, that this is really last resort, at least from the technical side. So this would be, if we discover it very late, technically the last thing we can do. But this is definitely something we would want to clarify beforehand. And then you have on the lower right, you have other concepts. This is called laser beams. It's basically mirrors that reflect the sunlight and focus it in one point on the surface of the asteroid, that the surface evaporates, and by this push also acts like a little engine and moves away. There are also a bunch of other ideas like painting one side of the asteroid so that it has different thermal properties, or gets pushed by the solar wind, and but they all take a bit more time, so I'm not going too much into that. But just to give you an idea what we have out there. One important thing to stress, all those technologies work great on paper, but we haven't tried any of them out yet. So this is also something we would like to do. And I'll come to that in a second. So sometimes you will come across headlines like this, be it in newspapers, be it on social media, and the bottom line is really like causing fear, more or less. Oh, what's going on? There's stuff happening. Is an asteroid coming? Is it going to hit us? What if NASA is wrong? As far as I'm concerned, those are all fake news. So I want to make sure that you understand, if you see any headline like this, it's probably fine. If there's really an asteroid coming your way, you would read it in every newspaper, and it's going to be announced by the United Nations, space agencies, everybody would be talking about it. We know if we have close flybys of asteroids, which happens a lot because we keep looking and we see, oh, there's an asteroid flying by. Take the one from the 29th of April, where it said like, oh my God, there's an asteroid coming towards Earth. Yes, but if you read the small print, you will read that it will fly by the Earth in a distance 10 times further away than the moon. So there's nothing to worry about. Of course, newspapers want to get sold, so they come up with scary headlines. But here it's best to ask, like, oh, is this really true? Because we know the orbit, the ones okay, there are many asteroids we don't know, so there's always a possibility that something could happen because we haven't found all of them yet. But the ones we do know, we know the orbit good enough to really say, no, we are very sure this is going to miss. Because remember, all of the ones we discovered so far, they're going to miss us in the next 100 years. There might be early observations where we need more to say, like, oh yeah, this one has a probability of hitting, but it's always a probability, and so far the more we observe it, the better our model of its orbit gets, and so far we can exclude them all. But again, we want to be prepared. That's why we're doing this. So there's still many out there. What can we do about it? So there are two projects on the way. On the left, it's an Earth-based telescope, the Large Synoptic Survey Telescope, which has a very large mirror. Not sure how large, but it's at least 8 meters, if not 22. So I'm not quite sure, but it's quite a big mirror. And this one will really help in discovering more asteroids. Of course, ground-based telescopes, you can only look at night and look for those objects. And for example, the object from Chelyabinsk, we didn't see this one because it came from the day side. So, and this is where the project on the right comes in. It's called NEOCAM. By now, it's been called by NASA the NEO surveillance mission. And that's an infrared telescope that will be put in space. And from there, we can also observe asteroids that are on our day side. So we will cover the other side of the sky, which will help us in discovering more and more of those objects until hopefully in a few years then we know them all. I mentioned earlier that all those deflection technologies haven't been tried out yet, but not for long. The Kinetic Impactor will be tested next year in 2021. NASA has the DART mission, which will fly and impact a moon of an asteroid. The asteroid is called Didymos, and it has a moon. And we know the orbit of this moon very well. Both of them don't pose any danger to us, but by flying and impacting with the moon, and then measuring the change in the orbit around its asteroid, we can calculate precisely how much energy was transferred and how well this technique would work. And 2 years later, the Europeans, with the European Space Agency, they have another mission called Hera. They will fly to that moon and then take detailed measurements of the crater that was done. So we get even more and other things, but we get even more information about how well this technology works, and that will give us a lot of feedback to know how to use it. Because once we know how to use it, we hopefully can avoid the fate of the dinosaurs, which is being wiped out. Because some people say the reasons the dinosaurs got wiped out is because they didn't have a space agency. And that concludes my talk. I hope that gave you a good introduction about the topic of planetary defense. I thank you very much for your attention. And I know this will be posted also on Facebook. And feel free to post some questions, and I will be happy to answer them. And yes, so please send your questions and celebrate Asteroid Day. Thank you for attention.